Thank you. So I'm going to introduce the discretization and analysis capabilities in Trilinos. And since I think outside of Sandia, this is probably the least used among all the Trilinos packages. So I decided to make really a high-level introduction of this. So what kind of tools do we have? So we have utility tools for automatic differentiation and also a field dependency manager failings that I'll talk about later. We have mesh tools for generation, storage, adaptation, and also some level set, very efficient level set capability on these meshes. We have discretization tools, mostly for finite elements, but we also have some capability for finite volume and a mesh-free package based on moving least squares. We have time integrators, and then we have different analysis tools for sensitivities, numerical optimization, and uncertainty quantification. Okay, so this is just a slide similar to what Kurt presented at the beginning. I'm not going through these. These are the most of the packages that are in the discretization and analysis product, not all of them, but yeah, you have those here for a reference. So fortunately, this was supposed to be a really nice movie, but it's not. So I want to really use the iSheet model example as a way to introduce these capabilities. And yeah, here I'm listing the team of people working on this application. The code for iSheet modeling is called Mali and Pass-Albany Landis model. And for this talk, we focus on the finite element core of it, which is implemented in Albany, which is a finite element library that is built on top of Trilinos. And you see the main packages we use. We use more of these packages, but more than these. But these are the main ones. And so I'll try to go through these packages as I talk about the application. So the basis, the foundation is probably the Intrepid 2 package, which provides local discretizations. And so in particular, high-order finite element basis for their Lagrangian hierarchical serendipity basis. They span the RAM complex. So we have I don't know, neglect elements. We have Raviatoma elements and so on. We have orientation tools that allow us to match the degrees of freedom for high-order finite elements. We have mappings between reference and physical elements, quadrature rules, and also projection tools to go from a function to a particular finite element space or between spaces. And then more recently, we have added some kernels for integration that exploit the structure that you might have. For example, if you have tensor product elements, we can use some factorization, or if you use if we have extruded elements or affine meshes, these integration kernels kind of are optimized for these cases. So for the iSheet application, we mainly use nodal finite elements, but other application, in particular, here I have an example of Vlasov simulation in Camellia or like magnetohydrodynamic application, solid mechanics. They use more advanced kind of and higher order finite elements in some cases. Okay, then we move a step up and we look at the mesh. The mesh we use is stick. Alan Williams is the main developer of the package. It's a snapshot package, snapshot for into Trilinos. It provides capability for mesh storing the mesh for mesh data structure. In the case for the iSheet code, we use this a vertical extruded mesh. Basically, we start from a 2D triangulation that's usually it's very non-uniform, and then we extrude it in a vertical direction, so we end up with a mesh of wedges. And then another package that we use related to the finite element, the mesh, is the Panzer degrees of freedom manager. So when you start having like high order finite elements or a multiphysics problem where a different variable needs different spaces, or you have different physics in different part of the domain, it becomes quickly very challenging to organize, to order these degrees of freedom manager, and Panzer helps you with this Panzer degrees of freedom manager, and that's developed by Roger and Eric's here. Another pretty cool package in Trilinos is Phalanx, also developed by Roger Pawlowski. And it's basically a field dependency manager. So you can imagine if you want to assemble like a residual, like that integral of some conductivity times the gradient of u times the gradient of the basis function. You can imagine you can extract some evaluation kernels from that expression. For example, the gradient of u, the gradient of the basis function, and you can see how you can reuse that for these different parts of the code, different residual. And what Phalanx does is really organize these kernels, managing all the dependencies, and building this direct acyclic graph and manage all the dependencies for you. So Phalanx does more than that, but this is one of the main thing that allows you to reuse little evaluation kernels for especially, and this is especially useful if you have a big multiphysics application. Of course, if you have just one equation, it's not worth it, but in our case it is. And then we also have time integration capability with Tempus, developed mainly by Kurt, and it has several time integration schemes like BDF, Runge-Kutta, implicit, explicit, leapfrog kind of methods. It has allowed for adaptive time stepping, and also you can do adjoint sensitivity analysis also in combination with the automatic differentiation package, and as well it can interface with the nonlinear solver Knox and with the optimization solver ROL, and then now let's go back to the iSheet project, and I want to talk mainly on the analysis capabilities now. So in particular on the PD constraint optimization capability. So for iSheet project problem, it's really important to calibrate the model. And with calibrate the model in particular means that you want to estimate the parameters that are not known. But for example, the friction between the ice and the bed, and the way you estimate this parameter is to try to solve an optimization problem where you try to minimize the misfit between your solution U and the observation jobs. So you try to minimize this misfit, and so to find the parameterization theta of your basal friction coefficient. And this constrains to the flow problem. So could be, in this case, it's like Stokes-like kind of equation. So that's your constraint. You want your solution U to satisfy that equation, and you want to find the parameter that minimizes that misfit. And plus you have some regularization term. So the way we solve this is, and this is kind of what we get after we solve that problem. So in the middle, you have this basal friction field that has been estimated by solving this inverse problem, and you estimate and is such that the model velocity on the left is as close as possible to the observer velocity that you have. That's the second figure there. And so in this case, for example, we have 300,000 parameters for the basal friction, and in total we have 14 million unknowns. And so the way we solve this problem is using optimization problem is implemented by ROL, which is the rapid optimization library in Trilinos. And so in particular, we are using a trust region method. If you are not familiar with that, so essentially, trust region method consists of finding a typical quadratic approximation of your function in a particular in a region where you trust that approximation to be true, to be accurate. Sorry, and then you find the minimum of that quadratic function, and then you move and then you iterate and you move this trusted region, and you will increase it or reduce depending on how well it fits your function. And in order to solve these kind of methods, you need typically derivatives, gradients of your function, but also Hessian, reduced Hessian. And the way we compute these, and I'll show it in a second, it will be with the automatic differentiation and also adjoints. So in particular, it's fairly easy to use role in your application. What you need to do is, first of all, to define a vector and the typical operations that you would want to do to a vector, like sum, norm, dot product, scale it by a quantity. And for this case, we use a T-Petra multivector. I mean, in reality, we use Tira vector, but then a concrete implementation is a T-Petra multivector. And then, essentially you have to for every guess of the parameter theta, rho requires you to evaluate your functional and the derivatives of the functional. So one way, the way we compute this derivative is with automatic differentiation, in particular with the package Saccado. It's mainly developed by Eric Phipps. And essentially, Saccado works as implements this automatic differentiation with a operator overloading strategy. And so if you want to, so for every variable you have, it doesn't only store the value of the value of your variable, but also the derivative of that variable with respect to the parameters. And when you want second order derivatives, so like the Hessian, we use this kind of expression, and so use these nested derivatives in Saccado, which becomes like a two-dimensional array in this case, where you again store the value of the function, the first derivatives, and then the second derivatives. Now, Saccado provides specialization for Cocos views, so that to efficiently and all these derivative types. It can be quite complicated, and you can ask Roger if you want. Sometimes it's but you can lay out the derivatives in a way that's efficient for your architecture, and in order to boost parallelism. So another thing that it's nice about the role, the rapid optimization library, is that it allows you several customization and advanced features. So in this case, for example, we're not really excited about the convergence of this optimization, trust region optimization method. So we tried a couple of things. And in particular, one possibility, instead of using to define your derivative, instead of using a Euclidean inner product, you can use an inner product that based, for example, of the mass matrix, which encodes the matrix. And this is particularly important if you have non-uniform meshes, because different part of the mesh have different degrees of freedom, have different meaning, and so this helps a lot. And the other thing that we did was to use a preconditioner based on BFGS to precondition the reduced Hessian, and also another trick that's typically very useful is to initialize the BFGS with the Hessian of your regularization term. So if you can see that now if you, after we did these advanced methods, you can see how we improve like the convergence by a factor of 5 or 6. So this is another kind of example. In this case, we have Antarctica, and we found in this case 2 parameters we're interested in. One was a basal friction, and the other one is a stiffening factor, which essentially is a correction factor for your rheology. And for this case, we run these both on CPUs and on GPUs on Perlmutter. So first thing is that role really lets you decide what kind of vector to work with. In this case, we use T-Petra, and so all the linear algebra. I mean, T-Petra can run well on GPUs, and so that as well it uses your own solvers if you want. And so in this case, we use all the. I think for this we are using Belos with Mulu preconditioner, and so you can see. For this kind of the most expensive part is the Hessian part, because you want to compute the reduced Hessian, and that involves basically 2 adjoint solves per Hessian vector product evaluation. And you can see in, not surprisingly, as you go to GPU, we really squash the assembly time. And we reduce also the solve time at not quite as much as the actual assembly time. But yeah, this was mainly to show that I mean, we can run efficiently on GPUs. And then, yeah, that was it regarding the hash-rate problem. So the last thing is that, okay, so you see, so these capabilities, you like to use that. So how you want to, how it's best for you to use these tools in your application. And this I'm borrowing the idea from Mike Hero that used to relate these the Trilinos packages to Lego bricks, and you can compose them as is best for your application. And so I came up with 3 main cases. Of course, it's arguable, but so the first case is that okay, I have my say finite element application. I really like the advanced capability in Trilinos, and I like to use them, but I don't really want really to intrusively change my application. And so, okay, 1 minute. And then, and so one approach will be to use Intrepid 2 with a degrees of freedom manager, for example. And if you want to solve an optimization problem, you can use roll or PyRoll, which is it has a Python interface to roll. And I think Christian Glusen later will talk a little bit about that. And then there is a second case that we say, oh, I really like Trilinos. I like the model evaluator concept. This is automatic differentiation. Then in that case, you can add Saccado for automatic differentiation. You can add failings for managing the dependencies between the fields and tempos. And in this case, of course, it will require a little bit more restructuring of your application. And this is the approach, exactly the approach that I presented that Albany uses. And then finally is that you're really in love with everything Trilinos, and you're starting from scratch, and then definitely start from Panzer. I didn't talk about Panzer, but basically Panzer is a package in Trilinos that use all the other packages, and allows you to do. I mean, it's a finite element library. So from input output, it handles the mesh, then handles the discretization, the solvers, the nonlinear solvers, the sensitivities, and adjoint capability. So it's really, yeah, you can start from that. And we have a couple of codes at Sandia that actually are built on top of Panzer, like Tricard and Empire. And I think Roger talked about that before. Okay, so that's all. All right.
Thank you.